Hello everyone, do you hear me?
Yes.
Yes.
Okay, very nice. Okay. So probably wait for 1 more minute and then we start. Is there any question in this minute we are waiting? Is there any question that you may have? No? So this is lecture 5. No, 4. Yes, 5 and 4. Lecture 4. Okay. Okay, so let's start because I mean there is a lot of material here today, and probably people still coming. So today we are going to talk about classification. Oops, what's this? We're talking about classification. And oh no, I haven't shared content, right? I was already writing. Sorry. Now I'm sharing. Yeah. So so far, what we have actually introduced the elements of machine learning, like let's say how to model some data, how to control overfitting in several ways, and how to build, for example, a predictive distribution. And this is what we discussed yesterday about Bayesian learning. But all of this was in the context of regression tasks, and actually the same can be applied today for classification, actually. So the task here, the task of classification here is, for example, that you may have, for example, two-dimensional space. You may have, I don't know, points of different types. Let's say signal and background, or any other classes that you may think of. So these two classes, what you would like, as we were discussing in the first lecture in the slides, is to give a prediction. So let's say from this you want to give eventually a prediction for the class of a new point. Let's say. So for example, I have a new point, whatever, another color, green. I have a new point here. Here. So what is this point? Is this point red or blue? So how do we do that? There are essentially, so you can actually divide all the models that exist in the literature. You can divide it in three groups. So there are essentially 3 main ways to do this. Each of these, they have a different level of complexity, and also its own advantages and disadvantages, of course. Well, this depends actually on the scope of your study. For example, the first one is called discriminative function. So discriminative functions, the idea here is just caring about the decision boundary. So it may be, for example, that you want just to care about something like this, and that's it. And your scope finished there. There is no more insight that you want to extract. You just want to classify a point. Then there are probabilistic methods, and then there is probabilistic discriminative models, and there is probabilistic generative models. In each of these two, families of models, the idea is to make an inference, statistical inference, on the probability of a given class. Of a given class, given some input, let's say. No, so this is the difference. So now we are actually, we would like to assign a probability for a given class given a point. So this instead of being, okay, this is either blue or red, I would like to say this is blue with the probability of 80% and red with probability of 20%. Okay, and they both do this in a different way, but the scope, and we will see that, but the scope is the same. At the end of the day, the scope is to report the probabilities for the classes, right? So let's see examples. During today, we'll see examples of each of these families of or each of these three ways to do classification. So let's start with discriminative functions. Okay. Okay. So the simplest thing, actually, what one could think of is to do the following. So imagine you have. I will draw several times things like this just to make a point. So imagine, I don't know, I have blue points here, and I have green one here. And you may, by inspection, you may say, okay, this is probably linearly separable. So I may just try to draw a line like this, right? And the simplest that you can do is to do a simple regression, right? So you may say, okay, let me just propose something which is as a function of x and has some parameters, something like something like what we saw in the other lectures, no, something like this. Remember, when I write phi here, it is that this is in the feature space, which may not need to be the original input space. In this following sense, in the sense that imagine that let me put it in this way. Imagine that your originally input space is actually doesn't seem to be linearly separable, and then you may have something like this. So this doesn't look like linearly separable. But then if you are clever enough, if you come up with a smart transformation, you can actually transform this into a linear space, into a linearly separable space. Okay, so this sort of transformation is always in the back of your mind when you should always be in the back of your mind when I am writing models like this one. So I am proposing now to think of a situation where whatever the input space you have, you can transform it to some space, the space of phi here, which is linear, and then you can just apply a linear transformation. Okay, but this of course depends on your creativity, on your ability to identify what would be the transformation that goes from non-linearly separable to linearly separable. So assuming you are already in phi space, in this feature space, and then you can model this decision boundary that I draw here as a linear with this function in a very similar way, then a possible strategy is to say, okay, then decide for the class with a rule like, so this is a simple rule like, for example, the class of my input will be, for example, class 1 if my function, let's say, is smaller or equal to 0, and class 2 otherwise. Okay, I can just follow this strategy, no? So then I can say, okay, this looks good. Let me follow this follow this path, and if I follow this path here, I can well, first of all, let me say that if more than 2 classes, if you are in a situation where you have more than 2 classes, a successful, well, not let's say a less problematic strategy would be to say that for the class K, I have one function for each of the classes K, and of course one set of parameters WK. Let me put just the intercept separated, right? So this for class K, and K goes from 1 to, I don't know, K classes, let's say. Such that, so I build a function for each class such that the class will be equal to CK if f of k is larger than f of j for all j different from k. Okay, I'm just saying, like, I evaluate all these functions for all these classes for the point in question, and then I say, okay, I choose the class having the largest function among all of them. Okay, and then you can follow this if you want. And but then there is of course the problem of, okay, I am already parameterizing my decision boundary like this with these weights, but what are the values of these weights? I need to choose the values of these weights. And actually, imagine that. So how to optimize the weights, or I mean the parameters? I'm talking about this. Well, you say, okay, yesterday we saw, or the other day we saw how to do this integration. So why not to follow at least these squares fitting, or mean square error or something like that, right? So if you do this and then you insist that this is the correct cost function for you, then you may say, okay, let me build my cost function. And if I build my cost function, I will be something like this. So the cost function, by following this strategy, the cost function would be let me write it like this, 1/2, for example. This is sum over all the points of the following. Now I am explaining a bit this. So that would be the cost function, where Ti is the 1 to k scheme or parameterization for point I. So if you have 3 classes and the point in question has class 2, this vector is 0, 1, 0, right? So you remember from the first lecture. But this is the label. So those are this is the label of point I. For example, equal to if a point is class 2 out of, and you have 3 classes. While this guy here is just, you have, for each class, you have one function, no? As I was writing above. Is there any question so far? Please just interrupt me, because I am assuming that this is being followed, but you please interrupt what I'm saying, okay? And so I won't bother you with algebra here, but what you can what you end up doing, actually you can parameterize. Let me just parameterize f like this. I can collect all my weights of all my all my classes in a matrix, capital W, and the feature vector. So remember, this is this guy is a k, has dimension k times 1, because this has dimension d plus 1 times k, this guy here, and the phi has dimension d plus 1 times 1. Okay. So f is just a vector of k components, and I have collected all the weights of all the classes in a matrix, which is d plus 1 by k. All right, so if I do this and then I minimize, so let's say minimize this with respect to the weights, then I obtain the following. I obtain, by minimizing this with respect to the matrix of weights, I obtain the best or the optimum matrix of weights, which is, not surprisingly, a solution that we have already obtained before. That's why I'm not insisting here. The only difference is that here instead of being y, since I have a classification for every point in the 1 to k scheme, I have k outputs. Let's say I have pre-parameterized my data set, my classification data set, for having, instead of one output for a given point, which is 2, 3, depending on the class, I have for every point I have k components, let's say, and this is, all these labels are included here. So this is a matrix of label. So this matrix is n times k by k. Okay. So then what would happen if I apply this? You may say, okay, this is optimum weight, but actually there are many problems with this, and in practice it doesn't work. So in practice, It's not giving good results in general. It may happen that for a data set it works, but in general, you have you have situations like this one. So let me share here an image, or not this image. Yeah. Okay, I will just reduce the image a bit. So this is an image from the book of Bishop, actually, where it is showing how, by doing this exercise with 3 classes in a two-dimensional input space, what is happening here is that even though this exercise may be straightforward because the 3 classes are linearly separable, in particular, you may obtain, with a better model, you may obtain decision boundaries like this and this. However, by following the above strategy, you are obtaining these decision boundaries here, and you see that the region on which that assigns a prediction to the green class is smaller than what it should be. It's the green class is, if you want, underrepresented in the prediction. And all of these problems, so there are other problems with this, but the reason why this strategy is not so good is because by minimizing the mean square error or the least square solution or whatever, this is assuming that the output is Gaussian. Okay, so you remember, if you have a Gaussian likelihood, the mean square error is exactly the minus log of the likelihood, and then by minimizing this is like maximizing your likelihood. So the maximum likelihood estimate would be okay if the variable is actually Gaussian distributed, but we are talking here about not a Gaussian variable. We are talking here about a categorical variable. So categorical variables don't follow, of course, a Gaussian distribution. They follow, I don't know, a categorical distribution, right? A generalized Bernoulli or something like that. Okay, so there are better models. There are better models of the first group, of the first family here, like, for example, the Fisher discriminant, linear discriminant, or the perceptron, and we will cover this tomorrow. Well, tomorrow, no, in the next theory lecture, probably on Tuesday, because it is a special model linked to neural nets, but there are better ways to do it. Those are better models. And I am not entering into details of this. You can, well, we will see in detail how this works, but this is covered in the literature. What I would prefer is to talk about one of the most popular models of this first family, which is the discriminative function, which is decision trees. And this is actually we are going to base our hands-on session of Running Monday. We are going to work with decision trees. So we are going to see in detail how this works. We will try to implement from scratch a decision tree. Okay, so if there is no questions at this point, I start with this topic now. Okay, so let me take a situation like this. I was drawing this some moments ago before the lecture. Cut. Oh. So imagine you have a situation like this. So you have two classes of points. You have a two-dimensional parameter space, x1 and x2. So this is a two-dimensional parameter space here. And two classes, and then you want to design a classification for this. And by looking at the figure, this figure, then it may seem like pretty complicated decision boundary, right? So by looking at it like this, you say, okay, this a method like this one may actually not work at all, right? Or even if I design, there is a priori no way to classify, to separate in a straightforward way the two classes, because I may draw something like this, etc. So it is complicated, right? However, with decision trees, this is much easier. So the idea here of decision trees is to split the input space, to always do it in a binary way. According to some criteria that I will talk about. So, but you do this in a greedy manner. So by greedy here means that you are always making a decision based on the current state of your system, let's say. So you are optimizing the cut, if you want, based on the current state of the system, and regardless of the history of the procedure. So in a greedy manner, it's just like an iterative way where you at each step you take like the best possible path, and it doesn't necessarily have to be the optimum one in the long term, but it is the optimum one in the immediate term, let's say. So this is like for example, when you have this traveling salesman problem, right? So the traveling salesman problem is a problem where you have like in traveling salesman problem, where you have like a few cities that you need to visit, and you need to visit once each of them, and at each stage you decide to go to the closest city, right? But it doesn't necessarily have to be this path, the shortest at the end of the day. So something like this. So going back to this figure, a greedy way to do this is the following, and to split it in a binary fashion is the following. So you make, for example, split the variable with the value, some value that maximizes the representativity of some class, for example. So imagine that you now decide to, let me put this in another color. Now decide to have the following partition. So let me try to cut here. I have this first split. So if I have this first split, then I say, okay, what if, so here, this first split is like the optimum one, like taking into account some like a sense of purity. And then you say, if I split this, you say, for example, I am splitting x1. If this is larger than t1, then I have a decision. Say, if yes, I do other stuff. one, and then I do some action, and if not, I do another action. So for example, I may decide that x2 is going to be split on T2, right? So if yes, then I may decide, for example, this decision boundary. If not, I may decide instead to split again variable x1 and variable x1 is going to be split, for example, like this. Oops. Let me put it here, like this. So, and then I go to each region, and in each region I make the decision. So, for example, if this is yes, then I may say, okay, this is belonging to C2. For example, if X2 is larger than T2, so I am now focusing on this region here, then I may decide that this is a blue class, for example, because I am already reaching some level or some depth of the tree that I have decided, and then I say, okay, now the majority class here is the blue one, so I decide for blue, right? And if not, then the other class, right? And if on the other hand I am on this part of the tree, x1 much larger or equal T3. So what can I say? I'll say, okay, probably I will, if it is larger than T3, I can, for example, have this split here. So this may be T4. And if it is smaller than that, I can have, for example, T5. No? So then this part of the tree is going to be a bit larger according to my criterion. So this is, if yes, then I have split this in T4. If not, then the same variable x2 in T5. No, I am splitting here T4 and T5 are splittings of the second variable. And then if x2 is larger than T4, then I can say, okay, then this is probably, I'm talking about this region here. So then if this is the case, then I will decide for class 1. This is the red class. If not, class 2. And similarly, if x2 is larger than T5, I'm talking here now about this region, then according to the points I am observing, I will decide that this is actually class 2. And if not, this is class 1. So you do something like this. And as we will see on Monday, we will like write the way to make these splits. So what is the criterion for making the splits? They all have to do with some notion of impurity. Let's say the splitting criterion has to do with some measure of impurity, let's say. Impurity. And impurity in the following sense. So impurity, let me call this the proportion of class K in a node M, and node, I mean in the region M. So this is the proportion or refraction of class K in region M. So this is then just equal to the number of points in that region. You sum over all the points that you find in this region, and then you just I don't know, the indicator function, right? So 1 if this condition is obeyed. So I have this impurity that I have built that I can compute in all these regions, and then there are many measures. There are many ways in which I can use this node impurity. There are, I will show here only 3 different ways to use it. The first one, okay, this is the easy one, misclassification error. The misclassification error is just 1 minus this. But here I am saying that this is the k hat is just the class that maximizes the impurity. But then I can find the misclassification error. I can build, sorry, my misclassification error like this one. A second one, which is very popular, is the Gini index. And the Gini index is the sum over all classes of these impurities 1 minus the impurity. So note that if the impurity is 0 for one class, then this contribution is going to cancel, right? And the Gini index is maximal, sorry, where the proportion when the proportion is equal, is distributed equally among all the classes. And there is also, of course, as in many classification problems, the gross entropy, which is just in this framework, is this sum log of, which is having more or less the same behavior like the Gini index, in the sense that if P is 1, then the corresponding term is going to be 0. All right. Yeah, so according to this, so let's say that in order to make the split, you decide what is the value and the variable to make the split, and the value of this variable that maximizes one of these measures. And by doing this every time, then you want to you end up splitting in one direction or the other, at one level or the other. Okay. So this is the idea behind the decision trees. Is there any question so far?
Yes, I have a question.
Yes.
Because in order to do this, you have to previously create your regions, right? So you are just like
Create my what?
evaluating how good is your regions, your
Yes.
mesh that you have already created.
No, actually, what you do is to so you have your input space with all the observations, and then you say, I want to decide what is my first split, and then I have a grid of points. So I have for example, a 2-dimensional grid, and then I decide, I evaluate, for example, the Gini index of the split at every value of the first and second dimension. And when I do this, I create the first split. Okay.
Okay.
And then you have 2 regions then, and in these 2 regions you do the same. You go to evaluate the split, the Gini index, and just focusing on this measure of both dimensions at each value of your grid, and then you decide what is the optimal one. Does the best one lie in the x1 or in the second dimension? And then you do this separately for one branch and for the other branch, etc.
Okay.
Yeah.
Are you going to give an example later or something?
Since I am dedicating a whole hands-on on decision trees, I prefer to give the full example on Monday.
Okay, thank you.
And Monday is going to be, I think, almost exclusively dedicated to decision trees.
Sorry, Brian.
Yes.
I still don't understand how do you do then the first split. And for example, the first one, do you have the x1 axis, and do you have this x1 axis to choose your split?
So imagine that I have this, and I have a grid of. This is what I was trying to explain before. So imagine that I have this grid of points, and the I am using the the background of the of my nodes here in order to make. So this is the grid, right? So then I am having this grid here, and then I say, okay, for first split. So evaluate, for example, Gini index for all the possible points of the grid. It means I have a Gini index associated to this split. I have another associated to this one, and another associated to this one, and another associated to this one, and another associated to this one, to this one, to this one, to this one, and to this one. And then I choose among all of them what is the best. Okay.
Yeah, but visually, which will be the best?
Depending on your data point. So here, for example, it may be that this split here, the first one that I was choosing, was the one given the optimum Gini index, the minimum Gini index. Because by doing this, I have a purity, right? I have some value for this.
You are searching for some purity then.
Sorry?
You are searching for some purity.
I am building if I decide, let's say I am evaluating whether I do split here or not. And then if I evaluate the split here or not, I am already defining this region and this region.
Yes.
Okay, this region will have a purity, this other region will have another purity. The combination of these, if I combine this in the way Gini does, then I get a value for Gini. And then I may compare this splitting with the splitting here. And then I have this region and this region. And each of these regions will have a different purity. And by combining it in a Gini way, I may have another value for the Gini corresponding to this split. Is this value of Gini better than this value of Gini? No, then I decide for, you see?
Yeah.
This is very, I mean, it's time consuming in the sense that you need to evaluate at every, for every split, you need to evaluate all the points for every dimension. Of course, if you are now have a lot of dimensions, it's going to be very expensive, computationally expensive, but this is the way decision trees work.
Okay.
And once you have decided the first Gini, the first limit that you
the first split.
The first split, you compute again the same process to find another one, or
so then imagine that was the best one. Then I have already two well-defined regions here, and then I go to the first region. Let me say that this is the first region, and then I repeat the same. I evaluate the splits in all these possible points of the grid, and then imagine it turns out that the best split was this one. And by doing this one and evaluating purity here and here, I have reached some level of purity that I have predefined before. Let's say that I am stopping when more than I don't know 80% of the points have one class over the other. No. Then I am stopping here. When I stop here, then I go to the other region. And by going to the other region, I do the same. So by this region, then I do splits here, splits here. I evaluate what is the best. Imagine that it turned out that the best was this one. And then I need to repeat the same for this region and for this region. You see?
Yes. So the best genie can be in any axis, right? And you choose the best one.
In any of the axes that in any of the dimensions. Exactly.
Okay. And how do you know when to stop?
When to stop? So imagine that this is up to you. For example, one criterion is to say I will stop when I have 3 points or less in my region, or I will stop when the proportion of the classes in the region is the largest proportion is larger than, I don't know, 80%. Then I stop. Then this is up to you, up to you. So or I stop when I have reached some level of splits not larger than 10 splits. This is another criterion. So this is really up to the implementation.
Okay, thank you.
Yeah. Okay, so there are, of course, advantages of decision trees. The main advantage of this is interpretability, right? So, in the sense that it is very easy to know what is happening in your classification. So, advantages here. Interpretability is the first one, the most important one. And also this is the way we probably in our brains work, and the typical example that is given when explaining decision trees is the one of a doctor, where the doctor is evaluating whether you have some disease or the other, no, some class or the other, depending on a series of binary decisions. So do you have headache? Yes or no. Do you have fever? Yes or no. Then this sort of evaluating process, no. So this is a nice thing, very nice thing. And also that data doesn't need to be linearly separable, of course. So look at this complicated example I have given here. Then the linearly separable here is not the case. And it's also difficult to conceive a phi space that you transform from X to phi such that this is linearly separable. This is also very difficult by inspection here, no? So then it seems to be that decision trees is doing the job. Of course, disadvantages. It makes hard splits. It makes hard splits. Sorry. First of all, makes splits which are always orthogonal to the axis, right? And this may be inconvenient. This is an inflexibility, if you want, of the decision tree. And also hard assignments, because if you belong to one region, then you are already like assigned to this region, to this part, right? and hard assignments of the class. However, today, I mean, there is a research on decision trees today. This is improved by making probabilistic assignments. By making probabilistic assignments. Okay. In the sense that there is today an implementation of decision trees saying that, okay, then this split is 80% probable and this split is, so if yes, this is 80% and this 20%, etc. No? So you have a softening of these assignments by introducing some notion of probability here. So another disadvantage here is that a single tree is likely to overfit, to do overfitting. Imagine that, for example, your criterion is I will stop when I reach level 10, for example, but probably this level 10 is too much, and then your regions are too small, and then probably your decision tree will overfit. There is a cure for this. Solution for this nowadays is to rely on, let's say, how do you call this? Cooperative, I don't know, well, ensemble methods. Where you, for example, you propose several decision trees which are not very deep, or I don't remember how they call. I don't remember what is the name of a tree having only one split. But imagine that you combine several of these small trees, and you combine them in a smart way, and this will make a nice. This will make a model, an ensemble model, which is more robust to more robust against overfitting, actually. So one of these is decision forests, for example. Okay, but this, I mean, I have no time to cover these ensemble methods. However, if you now go to decision forests because you don't want to overfit, because you want to do something more robust, then you are somehow losing interpretability, right? Because you can interpret a tree, but to interpret a forest, then it's much more complicated, because the result of a classification of a point is the let's say the combination of how different trees are actually classifying these points, and then the whole interpretability that we have in our minds is kind of lost. No? Okay, so so in general, all this family of models here, which are non-probabilistic, let's say that they may not be convenient if your scope, depending on your scope. For example, imagine situations where discriminative functions as decision trees may not be convenient. For example, imagine a situation where imagine that you are a doctor. Let's say, imagine that I have a decision. I want to make a decision depending on the probability of some class. For example, if the probability of a class is, I don't know, imagine that it is 60%. I don't want to make a decision right away because I may not be sure that this is the correct decision. So I may, depending on this probability, I may decide to take a look at this later, or to call an expert to, like, let's say, have a visual inspection from an expert, and not letting an algorithm to decide for me. So like for example, a trivial example is again a medical application where if you have the probability of having a disease of 55%, I mean, then probably you may be it's not too clear to make one decision or the other, right? And of course, there are other situations where you are actually interested in the probabilities and in the way that, for example, I am interested in the probability for this event to be signal instead of background, because if it is clearly signal, for example, if the probability turns out to be 90%, then I am pretty sure about the result and I am confident, and then I can do, I don't know, statistics on that. But it would be less convenient that there has an output of this algorithm. I just say, okay, this is signal, but imagine that it was signal with 52% probability, right? So obviously in physics, this is much more motivated. The probabilistic interpretation of classification is much more motivated, right? Another situation, so first of all, would be you are inherently interested in probabilities of given class. Another situation is, imagine that you want to penalize misclassifications you want to penalize more misclassifications in class A than in class B. How would you do that? And this is again an example which is typically shown in the medical framework, where, of course, you want to penalize more false negatives than false positives, right? This is more serious, no? So how would you do that? So you may design something like this. In order to do that, you may design a particular loss function. The particular loss function, for example, may be, for example, if this is the A and B here are the true class, and here I have the predicted class. Is A and B. Then, of course, some loss function may be, if I am penalizing more, for example, the misclassifications of class A, I may just put here a much larger number than here. So here I am classifying as B, something which is actually class A. And for me, this is much more important to avoid than the misclassification of class B here. So the way to do this, the most convenient way to do this is by minimizing the expected loss. By minimizing the expected loss is the following. I sum over K and sum over some region, I will tell what the region is now, of this matrix weighted by some joint probability for the class and for the input. Where here I am saying that, okay, imagine that I have a two-dimensional input space, and then I have a region 1 and region 2. So here, by doing, let's say, what I'm saying is that this expected loss should be like a marginalization of all my possible variables. So I am marginalizing over all possible classes by doing this sum, and I am marginalizing by all possible values of x by doing this integral. But this integral is divided in regions, so there are the points belonging to region 1 and points belonging to region 2, and that's why I am summing over the regions here. Okay, so the correct way to take into account a, let's say, a loss function like this one is to minimize this loss function. So what we are actually hoping is to look for the region that actually minimizes the assignment of region that minimizes this. Okay. And then if you do this by doing the above, you end up concluding that the best region here is the one that minimizes the following object. Okay. So going from here to here is nothing. It's just re-expressing the joint by this conditional times this one. But this is the same for all regions, so it can be dropped. And by doing this, you are actually realizing what is important, what is the convenience, sorry, of making a probabilistic approach, because this is the object. This is the object you are after. And if now you decide to change your loss function here, and your matrix is, instead of being 1001 is 10 and 1, because now you decided that it is not that serious to misclassify some class, then you don't need to build this again. What you need to do is just out of this, or to train to do the training such that this is built. You just need to take the same training, and this is the result of your training, and minimize this object with the new loss function, let's say. So this is what training is. And then by considering a new loss function, you don't need to do the training again. So you don't need to train again if L changes. Okay. I will just put a last situation where it is convenient to work in the probabilistic approach, and it's a situation where you can compensate for unbalanced data. For example, imagine a situation where you have only, I don't know, 2 points, 3 points here, but you have many more points of the other class. No? Imagine a situation that this is 99% of all the points, and this is only 1% of all the points. Then you will have the following. If you build like a dumb classifier that's saying that everyone is red, everyone is green, then you may have the impression that your classification is 99% accurate, right? But it is not, because it has completely lost the blue points, right? So then how do you deal with unbalanced data like this? It is convenient to deal with that in a probabilistic approach by, so imagine that you assign prior to each class given by the fraction of points, number of points, no, given by the fraction of points of each class. And then strategies first, you balance artificially, you balance the data. then estimate the objects you are after, and then correct with the priors. So you undo the balancing by taking into account this these priors, right? And this is because you know that this guy is proportional to this one. So that would be the way to go, and the best way to handle a situation like this is to just to balance the data set and think of it in a probabilistic term. Okay, so is there any questions so far? I'm trying to convince you here that by having a probabilistic interpretation is a good strategy, well, of course, depending on your scope. But even if you're a doctor, medical doctor, I think.
Can I ask a question?
Yes.
To me, it seems that decision trees are extremely slow or extremely costly computationally to begin with.
What?
The decision trees. If you have to do splittings in many dimensions and many times and for many branches, it seems that they are extremely slow to get any significant result that you cannot get with other methods. So what is the real advantage of other than interpretability? Or are there some cases that you cannot use any other method, or no other method is optimal?
I don't know. I mean, it's probably hard to answer this question. In practice, decision trees has been by far the most used method in collider physics. So they are using decision trees since the 90s, when the period of LEP, in order to classify events. So these events are very the input space and the events there of each class is a very complicated system, and they have been doing this successfully over the last 30 years. They are still doing it. So many of the applications in collider physics still nowadays are using decision trees. Does it mean that it is the optimum method? Probably not, but it's giving very good results. And at the end of the day, if you don't have a very, very large number of dimensions, say imagine you are working with 10 dimensions, and okay, you may have, depending on how fine is your grid, of course, but what I'm saying is that at the end of the day, with the present computers, this is expensive, but not that expensive. It is a tractable problem.
Okay, thanks.
Yeah. Yeah, I mean, for me, it would be hard to. What I'm saying is, imagine I prefer to model this problem or to decide on this problem with a neural network, and the decision boundary here is pretty complicated. So I probably need a lot of neurons in my hidden layer or something, and the training may also be slow because the network may be high. So but this example, by splitting your input space in this manner, then it is very fast. Here only 2 dimensions, and only I don't know, a few splits were needed in order to to find some convergence that you have predefined. So it really depends on your scope. Yeah.
Okay, thank you.
Okay. Is there any other question? So if not, let's do one thing. Let's take a 5 minutes break, and we come back at probably 20 past or something, if you don't mind.
Okay, thank you.
Yes.
See you.
Okay, so let's continue. Do you hear me here?
Yes.
Okay, thanks. Let's go now to probabilistic approach. So remember here from the first lecture, remember the way we know how to handle a random binary variable. So you remember it was if my variable is t, remember it was by a Bernoulli distribution, which was of this shape. Sorry, this is 1 minus t, where mu is the true unknown probability for t equal 1. Let's say, and this is the value we want to estimate at some point. And also for the case of a categorical variable, instead of binary, a categorical variable with k classes. Now let me put the variable in this one-hot encoding fashion, or this 1 to k scheme. Then you remember that we wrote something like the generalized Bernoulli or the categorical variable. Depending on the author, it is written in a different way. It is named or in a different way. But this is just the probability. Sorry, this is the multiplication over all classes of mu k to the tk, where tk are just the components of t, right? And of course, each class has one associated true or known probability, no? So in probabilistic approach here, the idea is to infer. So the idea here is to infer mu k. This is always the object we are after here. And then we do this by estimating. So you estimate the probabilities of the class ck given some input here. So imagine that you have a data set. So suppose a data set which consisted on some d-dimensional input space, and for each of them I have this binary vector ti 1 to n. Then the likelihood of the data, so this is the likelihood, can be written like this. How to put this? Okay, the likelihood, if I have a number of parameters, w, would be the multiplication over all the points of this probability here. And this probability here is just the multiplication over, I will put it a little bit smaller for you to see it, k1 to k. And I am identifying mu here. I am identifying mu with p, the probability for the class given some input to the ik, sorry. So I am identified, if you want, mu k with this. This is a central object in the probabilistic approach to classification. And of course, I forgot to write the dependence on the weights or on the parameters, which is here. So in a way, a classification model, a probabilistic classification model, is a proposition for this. Sorry, too fast. Proposition for this object here. Okay. For example, a neural network. Okay, then a neural network will actually, the output of the neural network is actually the probability for the class CK given some input. This is the output of the neural network, or the output of another model, logistic regression, something that we are going to see today. Okay, so then these probabilistic approaches, they were divided, as I showed you before, in like two type of models. The first one is a probabilistic generative approach, where instead of, so the idea is to, in order to model this object, what this generative approach does is to model this object first. This is CK. And then with this, it goes to the object we are interested in at the end of the day. So this is nothing more than this is the likelihood of point X given given some class, given CK, right? So it is a more informative way, in the sense that it is giving you a lot of information. Of course, you end up assuming a lot of things, but the idea is to use the Bayes theorem in order to do this transition. So the idea is that you have this because you first build your likelihoods, and then you know that with your prior, you are able to build what you are after at the end of the day. So this is like the first step. Okay. So now let me put an example. So consider two classes first.
I don't hear you anymore.
Me neither.
And he doesn't hear us.
Maybe we can like do something.
Yeah.
Maybe writing in the chat.
No, doesn't seem. I don't think he can see us either.
Maybe a video or something.
Oof.
Brian, can you hear me?
Maybe if all of us switch on the camera and do things like,
Yeah.
"Hey, we are here," he realizes. Personally, I don't have camera here, but if some of you have. Good one, Raquel.
Do you hear me now?
Yes.
Yes. Now
Yes.
yes.
Now we can.
I don't know what happened. Sorry, guys.
No, don't worry.
I got disconnected for some reason. So you can always what I'm saying is that you can always rewrite your generative problem in this way, in the way of making of putting like the argument of a sigmoid here.
Yeah. The thing is, we haven't been able to hear you for a while, so
From the first,
know.
from the example.
yeah. I was copying the base theorem, and I suddenly got cut off, so I didn't.
So from here,
We don't see the
From starting the example.
Yeah, we don't see the.
the tablet.
mhm. So you lost connection. I mean, I lost connection when I was talking about this.
Yes,
Yes.
just after writing it.
Okay, so fine. So consider what I was saying is consider the example of two classes, and in the example of two classes, what you are doing is to write the probability for class one given some x here will be given by the likelihood times the prior divided by this, because I have only two classes. So remember, this is a normalization of the numerator, or marginalization over the classes. So I have this one, and I am just rewriting this as in this way. So I'm dividing the numerator and denominator by the same thing. So I can rewrite it in this way. And by defining what is this, by defining A like this, the whole expression here is can be put in this shape, which is nothing but the sigmoid function. Okay, the sigmoid function, if you probably know it, is just has this shape here where it goes to 1, or it's a bounded function from 0 and 1, and it crosses the axis at 0.5. And what I was trying to say is that all the every generative model can be like reparametrized as I mean, the argument of a sigmoid, let's say, at least in two classes. Okay, so this is a generic result, no matter what is your model behind your likelihoods. You can always write it in this way. And for more than two classes, there's a little bit different, but very similar expression, which is, okay, I now apply my base theorem. So this is likelihood times prior. But I have k classes, so I need to sum over all the classes. J, PCJ. Okay, this is the generalization on that. And by defining some quantity AK here, which is just the log of this likelihood times the corresponding prior, I am able to rewrite the whole thing here as e to the ak over the normalization. And this is nothing but the softmax function, which is a similar function or generalization of the sigmoid for the case of more than two classes. Okay, so let's now put an example on that, an analytic example on this. So, for example, suppose, so the message I'm trying to transmit here is for a generative approach. You first need to define what are the likelihoods of your input, right? And then suppose we say that, okay, my input is continuous, and suppose it is Gaussian. So then I write the probability of a multivariate Gaussian, because I am in D dimensions in general. I just write my multivariate Gaussian, right? So I am just writing here the exponent part. This is, remember, proportional to the exponent of x minus mu k, and this is the mean associated to the class k multiplied by some the inverse of the covariance matrix times the same, right? So let's assume the same covariance matrix for all the classes, just for simplicity. And of course, this mu k characterizes the class. So by assuming this, I compute I compute this guy here. For example, in the case of two classes, A is just the log of P C1 minus the log of P of X given C2 plus, okay, the log of the ratio of the prior But if I do this with this expression above, I end up being able to express A in the following way. This is just one single line that I have not written here, but it's very straightforward to obtain. Minus 1/2 mu1 transpose mu1 plus 1/2 the same for mu2 plus, of course, the log of PC1 over PC2. So the whole thing can be written in this shape. I mean, as this. So you see here, this is some function, some prefactor here of that multiplies x here, which enters linearly, plus some independent term. Okay. Then, in general, I see that by doing this, which I can always express in this way, as I demonstrated above, this is the sigmoid of, the softmax plus WK0. And this implies a linear decision boundary. So every time, even though you have a complicated function here, which is a nonlinear function as the sigmoid, every time I have x entering linearly in the argument of this sigmoid, I will have a linear decision boundary. Okay. Of course, this is possible because I have obtained, I have assumed the same covariance for all the classes. But, it may not be the same if I don't do it, as I will show you later. But if I assume the same covariance, then I can express the argument of the sigmoid in a linear fashion. And this implies that the decision boundary among all the classes is going to be linear. So is there any questions so far? Okay. So what the idea here now is to fit, of course. Now you need to fit or to find the optimum values of your parameters, right? So then you maximize your if you want, you can maximize this object at the end of the day and follow this. But I prefer, in order to be, because I'm already a bit late, I prefer to go to a specific model of generative probabilistic approach that is going to be probably very useful for you. So I prefer to spend time on this and not to obtain more theoretical results. But it is important for me to know if there is any question so far. Okay, so let's see an example of a generative model. Is so-called naive Bayes classifier. So here the idea is the following. The idea is to assume that given a class, each component or each feature, if you want, so let's say I have D features, right? Each of these D features, they are independent. They are independent from each other. In other words, I am saying that when building this likelihood, this is just the multiplication over all the dimensions of my data set of this. And this is a condition called, this is something called conditional independence assumption that actually determines the naive Bayes classifier. Then, once I have written for all the classes, once I have written my likelihood for all the classes, I can go and write the object of interest, which is this one. And so this is the likelihood, but the likelihood is just what I wrote above. Right? Times a prior. So idea is to compute this for each k, for each class. And then for a new point, I might imagine I have a new point x new. We choose the class that maximizes this. We choose the class that maximizes the posterior. The posterior. So I'm saying is that the class of x new, I'm just trying to write what I just wrote, is the Rmax of this. We can see how this works in the following the notebook. But is there any question on the philosophy of the naive Bayes model? Okay, so let me share screen. This one. Do you see the screen?
Yes, yes, we do.
Okay. So imagine I have some data that I will actually use later for when introducing neural networks. But imagine I have generated this synthetic data set. I have 3 classes. I have 2 dimensions. And these were generated actually from sampling from 3 Gaussians with the means located at different points. Let's say one mean here, one mean here, and one mean here. Standard Gaussians, I'm saying that the standard deviation is 1. And I have, and this is important, I have, for example, different number of points in my data set depending on the class. So I have 500 for the first class, 300 for the second class, and only 100 points for the third class. Okay, so I have a data set like this. So this is a 2-dimensional data set, and then I have the output for each of them being 0, 1, and 2, let's say. So the first thing that we need to do is to get the means of each class. In other words, you get this mean vector characterizing each of the classes, which is nothing but take for one class, you take all the points and you get the mean. For the other class, you take the points, you take the mean, like the centroid, right? And this is what I'm doing here by getting the means. The input of this is all the data set and all the outputs. All the outputs are here, and the number of classes. And I'm just computing for each class, and I'm computing the mean of all the points belonging to this class, if you want. And when I do this for this data set, I obtain this. Note that for the first class, I have obtained something similar to 0 and -2, which is exactly the case. So it was I mean, let's say that the generated Gaussian that I use for generating this data is actually close to this one. And this is the mean for the other class. For the second class, is around 2 and 2, 2,2, and then this is exactly what was the case. And the third class is like the centroid of this class. Third class is -2 and 1.8, where originally it was sampled from -2.2. So it makes sense. Then, as a second step, what I need to do is to compute not the means, but the standard deviations of each class, because I need the Gaussians for each class. So those are the means and the standard deviations for each class. So I do exactly the same as I did for the means, but instead of storing the mean, I store the standard deviations. And when I do this for the data set, I obtain 3 standard deviations. So you remember that the conditional independence means that there is no covariance matrix here. It is only variance for each dimension. So each of the classes will have 2 variances or 2 standard deviations given by the 2 dimensions of the data set. So the standard deviations of the 2 dimensions corresponding to class 1, to class 2, and to class 3. The 3 of them, I mean, all of them, they are close to 1 because I have secretly generated my data set with the standard normal. I mean, this is the way to generate, to sample from a standard normal, which by definition has a standard deviation 1. So all of this is reasonable. Then the next step is to get the priors of each class, which is nothing but the fractions, the fraction of points of each class. So I just compute here how many points I have of each class, and then I divide by the total number of points. And if I do this for each class, then I get these fractions, which are corresponding to a data set consisting of 900 events, sorry, 900 points. So more or less, this is reflected here in the priors. Now the interesting thing, or the place where you do also your assumption is by computing the likelihood. So I'm just writing here the log of a Gaussian, nothing special. Given mean and standard deviation, I compute with this log L the log of my Gaussian. And I use the log of the Gaussian in order to compute the posterior, but this is actually not the posterior with normalization, but the unnormalized posterior, if you want, or the joint. So which is nothing but, so the log of the posterior is just the log, the sum of the logs of all the likelihood plus the log of the prior. But the log of the likelihood, since I have assumed conditional independence, it is just the sum over all the dimensions, and there is a Gaussian for each dimension here. Okay. Then I have all the ingredients to make a prediction, actually, because my class prediction is first of all, I need to compute for all the classes. I compute what is the posterior for a given point x nu. This is an input. And then I compute the posterior or the unnormalized posterior of each class. So each class here is just this I is runs over all the classes. So I have here the mu's of all the classes, the sigmas of all the classes, and all the priors. And the decision is made to classify the point to be the classes, the class that maximizes this object. So in this object, I am saving, if I have 3 classes, I am saving 3 numbers corresponding to the posterior of all the classes given the point. And then I'm just choosing the class for which the posterior is the largest. Okay. And the results are here. So I have the 3 classes, and I have okay. I mean, this is a shitty way of plotting, because I have these regions in these blank regions here, which is just my fault not being able to draw this correctly. But forget about the color of the background. Just the decision boundaries are what they should be, more or less. Okay. So note that this is a very powerful method, and it requires nothing as a computational. It's not computational expensive, in the sense that I haven't optimized anything here numerically, like the case of a neural network, for example. I haven't done nothing like that. I have just computed. I have characterized, if you want, these 3 populations, and then I am assigning for a new point. Let's say I have a point lying down here. I am assigning, I am computing the posterior corresponding to each of the classes after my characterization, right? And then I just decide what is the largest of the posterior. So, is there any question here? No questions? Okay, so note that it may seem to be a model giving you linear decision boundaries. So again, forget about this shitty way of plotting, but this seems to be like a linear decision boundary, but it doesn't have to be necessarily the case. And actually, this is the case only because I have all my standard deviations here are pretty similar, and they are similar to 1, because I secretly generated my data set being from 3 Gaussians having the standard deviation 1. But and this is something that we obtained in the notes some minutes ago. Shall this not be the case, that the 3 populations are not having the same standard deviation or the same covariance? Then you have a situation, for example, where one of the classes has a standard deviation 2, and the other 2 classes has a standard deviation 1. So I'm just changing the way I generated the first class. So now I think the first class is the purple one. And just by this, I mean, by doing this, of course, the standard deviations I got are different according to the class. So these 2, they have similar standard deviations, but definitely the first class, when I compute it, I have a standard deviation which is different from the rest. And when I repeat the procedure here, the result is this one, right? So, which demonstrates the fact that naive Bayes is not inherently a linear model, but it's actually depending on the assumptions of your likelihood. Okay. So once I let me go back to this problem here. Then I just need to compute the accuracy, the global accuracy, which is I compare my predictions to my actual observations. And then, okay, in this particular example, I got a classification rate of 98% also, which is acceptable, let's say. But I mean, of course, this data set is easy in terms of it is easily separable. But this model, this naive Bayes, I mean, I personally consider it as a baseline model with which I compare other more sophisticated models as a neural network, for example. I first always try to say, okay, what is roughly speaking the separability that I obtain from this data set? I use an Naive for that, because this is roughly the order of magnitude. I mean, the order of the classification rate I should expect. Okay. Any questions?
Yes. Yeah, I wanted to ask if there is a way of calculating the error of your classification given a point, because I guess that if the point is in the middle of the two lines, you have a larger error, but if it's close to the center, it's better classified. But...
Yeah, indeed. So that's a very good question. So these points here at the very, I mean, middle of this region, or even the farther away from the other boundaries, will have a classification, a probability for belonging to the purple class much larger than the points closer to the boundary. And a first guess on that is the following. So imagine you are in the case of two classes, and then you know that the class itself, you have been modeling it by a Bernoulli distribution, and with your model, the only thing that you have done is to estimate what is the probability of each class of a class given the value of x, which we see we are identifying with the parameter of the Bernoulli. So in other words, the output of this classifier, of this binary classifier, because we are thinking in a binary problem, is exactly giving you this mu of the Bernoulli. So you know that the expected value of the Bernoulli is mu, but you also know what is the variance of your Bernoulli, and the variance of the Bernoulli is mu times 1 minus mu, as we saw in the first lecture. So this is already giving you, roughly speaking, what would be the uncertainty on that, because it is a special case where uncertainty is depending only on the same parameter. So in Bernoulli, both first moment and second moment, I mean, all the moments, there is only one parameter here. So by determining with your classifier the value of mu, which is the probability of CK given x, you can have access not only to the mean probability, but to the variance of this.
Okay.
Yeah, that would be a first way to do it. A rough way to do it. Of course, let's say there are more refined ways, but that would be a first guess, let's say. So in that sense, these points here close to the boundary, they may have a large. So the point on the boundary actually, for a binary problem, has a. Imagine this is if mu is 50%, right? Then the variance of this is 50% times 50%, because it's mu times 1 minus mu. So it is 0.25. This is the variance. So the square root of that is giving the uncertainty, which is again 50% or so.
Okay.
Yeah. So this may be a short answer, let's say.
Okay, thank you.
Any other question regarding naive Bayes? Well, if not, please. I mean, I also lost some minutes with this lack of connection. I am only 2 pages left. I have only 2 pages left for finishing my lecture. So if you don't mind to stick with me 10 more minutes, I would appreciate it. Okay, so let me share screen. Then we can actually just dedicate the whole Monday to the hands-on and forget about the theory. So in the last minutes, I promise it's not going to be more than 10. I wanted to show an example of probabilistic discriminative model. Okay, and the idea here, this is also a probabilistic approach, but the idea here is going directly, so directly inferring this without defining this first. So in a way, I'm going directly from data, I am directly like estimating this object without the need of proposing a likelihood for that. Of course, there are advantages to that, which are faster to train because we have less parameters to determine, and then other advantages. But depending on your scope, you may be willing to do it or not. For example, one disadvantage may be that, one disadvantage of a generative model would be that if you are following a generative approach and you assume something for this which is really not the case, then what you conclude for that may not be accurate. So then by following by directly estimating this may give you advantages on this in this sense as well. And I'm quickly going to the prototypical example of that, or the simplest example, which is logistic regression. And logistic regression is a very bad name because it is actually a classification model, not a regression model. So the idea here is to model this directly as, and this is something that we actually wrote previously. Sorry, this is x here plus the intercept, let's say. So logistic regression, by looking at this, it is a linear classifier because what I have told you, that x enters linearly in the argument of the sigmoid. So this is a linear classifier here. Then, okay, just let me rewrite this as a compact way of rewriting this with my feature vector. Remember, now by writing this, by going from this to this, I am assuming that I have gone to a phi space, because in general, this is something that you may evaluate to do before any classification. You may go to a different space where the classes are more separable, let's say. No? Okay, so the way to go to train it, you minimize the cross entropy. So remember, cross entropy, it can be written in this way. So this is the log of the likelihood. Let me write the likelihood in this term, in this way. So these are the matrix of labels, and these are the matrix of the weights here. So the matrix of labels in this one hot encoding, right? So, and we have written this actually in the first lecture. So this is minus sum over the data points minus sum over the classes of TIK log of log of my p of my conditional probability of the probability of ck given the input, but this I'm saying that the logistic regression is estimating the probability of for a given class by this function. Okay. Then if you write this and then you minimize it with respect to a particular parameter, sorry, with respect to a particular j here is the class. Then you end up having so let me just write that one line and then the result k of tik times 1 over. I am just now differentiating the log and applying the chain rule. Okay. And by differentiating then y, which is nothing but the sigmoid, then I get the following. This is only 2 lines. Okay, I have done nothing special here. Okay. But this is important for you to do it. Okay. Then I can just rewrite this to say what is y. So y is just my my sigmoid, right? So this is just this model here minus the labels. And that is a way to go. So, but this should be equal to 0. And because of this nonlinearity here, then the optimum parameter for each class will not be analytical, as it was in the case of regression, right? So what I'm saying is that this should be maximized. So this is our mean actually. It is a cross entropy. This should be maximized numerically. And then you need some iterative method, like you need, for example, gradient descent or something that we are going to cover later. But this is very simply what logistic regression is. Actually, we will see that logistic regression. So logistic regression is a very simple simplification of a neural net. There's a limit where, well, if you take no hidden layer, you end up having this without hidden layer. We will see this in the next lecture. And so, okay, and that's it. So I will we probably have to do the exercise in the hands-on session of corresponding to neural network. We are probably also exploring the possibility of having a neural network without hidden layer, and then it would be like having a logistic regression. Okay. So is there any question on this part? Or on any other aspect of the lecture? Is there anything that, okay. So two things. First of all, I was thinking about two homework here. So the first one is this one. This is a homework. And the second one was probably more fun to you is to take the notebook. Let me go to the notebook again, just to finish. To take the notebook here and play with the model. My face. Okay, so what you can do here, if you want, is to so there are essentially the thing is that with the naive Bayes there are no parameters here, in the sense that the means and the standard deviations are the ones that you have from the data set, right? However, I would like you to try to play with different data sets by generating different data sets and seeing what would be the result of the model, the performance of the model, by generating different data sets with different centers. I mean, I'm using the Gaussian centers here to generate the data set, and by exploring different, like in this notebook here, different standard deviations of the normal generating this type of these data sets, right? So I will share this notebook with you, with all the generating functions being replaced by this first line, such that you can play with the scale, and you can actually, for example, make a data set where the classes are more overlapped, and you try to do your naive Bayes on that, and then you try to draw some conclusions here. Okay. So if you want, the second homework would be to play with this notebook and try to see the performance on different data sets. Okay, but other than that, I have finished. I'm done here.
Okay, thank you very much. See
Okay.
you Monday.
Okay, see you on Monday. Thanks.